The Internet of Things is driving change, and embedded platforms are rapidly becoming smarter and more connected. These attributes challenge developers to build increased functionality and yet do so in smaller form factors with minimal power consumption. One way to meet these challenges is to consider carefully the clock architecture. Microchip's MEMS-based clock generators synthesize multiple frequencies from a single integrated reference. A tiny MEMS resonator and oscillator create a precision reference source that drives a programmable low jitter synthesizer with multiple stable clock outputs. To understand how a clock generator benefits a system design, let's take a quick look at this touch panel design. The panel consists of a microcontroller core connected to a sensor with audio-visual feedback and 3 types of high-bandwidth interface. Many of these peripherals require a stable, low-jitter clock, and they're often at different frequencies. Traditionally, multiple crystals have been used to achieve this, but Microchip's clock generators provide a single-chip solution that simplifies design while also delivering significant component count reduction. Our MEMS clock solutions offer important advantages, and they're in packages as small as 2.5 by 2.0 millimeters. These tiny MEMS clocks achieve very stable frequencies over extended temperature ranges. The systems are electronically compensated for temperature, and that allows less than a 10 ppm frequency deviation between the extended limits of -40 and 125 degrees centigrade. By comparison, crystals follow an S-curve frequency relationship with temperature. A stable frequency is important, but it is also key to have a low jitter clock source. To understand this better, let's quickly review jitter. A clock creates a timing signal by its very regular periodic transitions. System noise causes slight time deviations on each transition. Some of them are early and some of them are late. This variation is called jitter, and it's measured in fractions of a second. In digital systems, jitter can cause data errors. In the analog world, it results in noise. Different applications can tolerate varying amounts of jitter. Microchip's clock generators have less than 2 picoseconds of jitter, making them an ideal fit for jitter-sensitive applications such as gigabit Ethernet, PCI Express, and video processing. Since the MEMS resonator is just microns in size and extremely light, it is immune to shock and vibration. In addition, the fabrication of our MEMS in a high-volume silicon foundry to semiconductor standards guarantees very low defect rates. We address the challenge of design cycles very well by having an online tool where users can program their frequencies and output logic protocols, and then they can instantly receive a datasheet and samples within a few weeks. A MEMS clock tree achieves a very attractive cost of ownership. The small size reduces printed circuit board footprint. Not only is the bill of materials reduced, the design time is also lowered because the need to specify and design multiple independent crystal circuits is eliminated. Further, the high reliability reduces field returns. As a final note, let me show you how the automotive industry is benefiting from MEMS clocks. Here, our DSE 2311 is controlling the video processing and Ethernet transmissions of a surround view camera and assisting safe driving. We've qualified our MEMS products to AEC Q100 standards. Let's now switch to the digital infrastructure and see how Microchip's 2 DSC 400 MEMS clocks are enabling a Cavium-based server in processing information packets up to 100 gigabits per second. The 2 MEMS clocks are providing a 50 megahertz reference for the gigabit transceiver and also the reference for the Zowie interface of the microprocessor. The DSC 400 has 4 independently programmable outputs up to 420 megahertz. To explore our entire portfolio of clock generators, please visit microchip.com/clocks.